Uh-huh. Good afternoon. This is Professor David J. De Los Reyes. Okay, I will now be on my topic, lesson number 81 on my channel. Oh, sorry for that one, lesson 82. Lesson number 82, Integral Calculus, volume, under the topic Miscellaneous volume. And the topic for this afternoon will be pyramid with equilateral triangle as the base. The problem is asking for the volume of an equilateral triangle base pyramid. Okay, so meaning the problem is asking for the volume as a function of S and H. The length of the equilateral triangle at the base is designated by S, and the altitude is H. So the problem is asking for the volume as a function of S and H. Actually, we have derived this one already yesterday using integral calculus. And actually, the formula for the derived volume is actually square root of 3 over 12 S squared times H. So by using the so-called derived concepts for cones and pyramids, we will try to derive this one. So meaning we will try to verify if the derived volume yesterday was correct or not. Okay, let's proceed. So derive the volume of a pyramid with equilateral triangle base, and the length of the base is S, and the altitude is H. Center point, vertical line, this is H. So the problem is asking, we try to verify if the derived volume yesterday, which is square root of 3 over 12 S square H, is correct. Okay, let's proceed. This is the 3D view, meaning we are in space, 3D. We are on the X, Y, and Z plane. So actually, we got an X-axis, we got an Y-axis, and we got a Z-axis. This is X, this is Y, and this is Z. That's why it is a 3D view. We are in space. Okay? So the figure will be something like this. This is S, S, and S, and this is altitude S. Okay? Let's try to derive. We try to segregate the base area. The base area will be something like this. This is S, S, S. It is an equilateral triangle. Okay, equilateral triangle. If we try to drop a line coming from this corner here, vertically downward. So if this is horizontal and this is vertical, we could say that this angle here is 90 degrees. And this also is 90 degrees. Okay? And in general, for any triangle, if we know the length of the base and we know the height, we could compute for the area. And area for a triangle is actually 1/2 the length of the base times height. So in here, we'll try to compute for H, because to compute for the base area, we should know this value here, okay, times the length of the base to compute for the base area. Using the Pythagorean theorem, capital letter H is actually the square of the hypotenuse. Sorry guys. Just take 1/2 portion for the number, 1/2. Okay. If we try to compute for this, it will be the square of the hypotenuse minus the square of this adjacent side over here. And the adjacent side, since the triangle is equilateral, if we try to drop a vertical line over here, this should be the midpoint. So if this length here, so if this is S, and this is the midpoint, actually this is S over 2, and the other half will also be S over 2. It's symmetrical. So h will be the square of this minus the square of this into the square of. If we try to simplify this one, h, the altitude of the base area. The base area, it's not the altitude of the pyramid, will be square root of 3 over 2 times s. Because if we try to simplify this will be 4s square minus s square over 4 or 3s square over 4. Take the square root. The operation inside are all multiplications, so if we try to take the square root, it will be the square root of 3, and the square root of s square is s, and the square root of 4 is 2. Or the height of the base area will be square root of 3 over 2 times s. So if we now try to compute for the base area, we are not using integral calculus here. It's just the normal solution, okay? It's the so-called solid mensuration solution. Base area will be equal to 1/2 times the length of the base times height. This is a general equation in mathematics. For any triangle, to take the area, just take 1/2 of the length of the base times height. Or this should be equal to 1/2. The base being mentioned here is actually this one here. The total base, the total length of the base will be s. It is this one. Okay. So the total length of the base is s, and the height is actually h, the one we computed, and that is actually square root of 3 over 2 times s. So this should be 1/2 times s times the square root of 3 over 2 times s. Okay. Taking all the product, 1 times the square root of 3 will be square root of 3, 2 times 2 will be 4, s times s will be s squared. So the base area for an equilateral triangle is actually square root of 3 over 4 s squared. Okay, let's try to recall another general equation for cones and pyramids. This has been proven to be correct. For cones and pyramids, the formula for taking the volume is actually 1/3, okay, the base area of the cone or pyramid times its height. This has been proven in integral calculus. Okay, so if we try to use this proven general equation, we will just substitute values. So this should be 1/3. The base area for equilateral triangle is square root of 3 over 4 s squared. So this should be square root of 3 over 4 s squared times. We are now taking the volume of the pyramid. So the height being mentioned here is x, the one given. It is this. Okay. So if we try to take the product, 1/3 times the square root of 3 over 4 s squared times h. 1 times the square root of 3 is the square root of 3. 3 times 4 is 12. This is s squared. This is times h. So actually our solution yesterday using integral calculus was correct. This was the solution yesterday. Okay. And by using the solid mensuration solution, by using the proven concepts for cones and pyramids, which is 1/3 base area times height, what comes out for an equilateral triangle pyramid is actually the volume is actually square root of 3 over 12 s squared times h. It is correct. You see, guys? Right? It's the same as yesterday. But we introduced this one. Where did I get this one? It has been proven in integral calculus, but for cones and pyramids, if you try to take the volume, it should be 1/3 the base area times height. Okay, I will try to give an example. Actually, we've been through with this one. For a cone, the volume is actually 1/3 pi r square h. Okay? The radius is r and this is h. Okay? That's a volume for a cone. So this is actually similar to the for 1/3 the base area times the altitude. The base area is a circle, right, for a cone. So actually it's pi r square. If the altitude of the cone is h, this should be times h. So actually what we use over here was correct. Okay, times altitude. For cone or pyramid, the volume will be 1/3 the base area times altitude. Okay, so this is 1/3. We try to verify the area of the base of the cone is pi r square times the altitude h. Okay, this has been proven under integral calculus. And for a square pyramid, actually we have derived this one already under integral calculus. If this is A, and this is H, we have derived already that the volume of this is 1/3 A square times H. Okay, this was derived from integral calculus. Okay, let's try to follow this one. Volume is actually the base area 1/3. What is the base area? If the base of the pyramid is a square, this is A, so the area will be A times A. Right? Times height. So volume is actually 1/3 A square H. We also derive this one under integral calculus. Also under integral calculus. So the concept that we use here is actually a proven concept. That for any cone or pyramid, volume will be 1/3 the base area times height. Okay, good afternoon, Los Angeles.